So hello everyone and welcome back to the good stuff we have been doing, and today in this video we're going to try to evaluate this beautiful integral using Frullani integrals, and you're going to see in a bit. I know that this may not look like something we are going to use Frullani integrals for, but you're going to just see. That is why we love mathematics. So to begin with, we're going to try the series part, because observe that this denominator, which is 1 over e to the x minus 1, you could always write this as, say, e to the negative x and then divided by 1 minus e to the negative x. So basically this will be the sum as n runs from, let's say, 0 to infinity. Okay, you have e to the negative x multiplying that, then you have e to the negative x all to the n power, then this will be the sum as n runs from 0 to infinity of e to the negative nx. Okay, I was about to write dx here, but there is no need to dx. This is not an integral, so you could express this into a series form, and that is the key identity to use this. So here, this will be equal to, let's change our pen, this will be equal to the integral from 0 to infinity. Now you have a sinh squared of x over 8 divided by x, then you have the sum as n runs from 1 to infinity of e to the negative nx, so you have a dx. So what we're going to do is that we're going to take the sum out of the integral, and then this will become the sum as n runs from 1 to infinity. Then you would have the integral from 0 to infinity. Then what happens next here? Here you are going to have sinh squared, hyperbolic sinh squared of x over 8. Then you have e to the negative nx all divided by x dx. So we are going to compute this integral in terms of n, and then we're going to take the sum. Okay. Now, what do we do here? Well, if you notice that the divisor of hyperbolic sign, this is of x, this is going to be e to the x minus e to the negative x all divided by 2, right? So this will be the sum as n runs from 1 to infinity. Then you would have the integral from 0 to infinity of the square of e to the x minus e to the negative. Okay, this will be x over 8 minus e to the negative x over 8 all divided by 2 all squared times e to the negative nx over x. Then you have a dx. So if you take the square, what happens? If you take the square, you end up with, say, this is the sum as n runs from 1 to infinity of what? This will be this integral right here from 0 to infinity. Though here now you have an e to the x over 4. Then you have minus twice, okay, you have a 1/4 here, obviously, you have a 1/4 here. Then you have minus twice, just 2, and then you would have plus e to the negative x over 4. Then you have e to the negative nx, all divided by what? All divided by x. Then you have your dx. So we can obviously trace the 4 out of everything so that we can focus on more serious issues. So you have n equals to 1 to infinity. Then you have the integral from 0 to infinity. Then in x over 4, so you have e to the x over 4 minus nx. So let's say x over 4 minus n. So that is x minus, let's say 1 over 4 minus n, that is 1 minus 4n over 4, right? Or let me just say x over 4 minus n. Let me just say x over 4. X over 4. So what? 1 over 4 minus n x. Yes, put it this way. Then you have minus, let's just say minus twice e to the negative nx. Then you have plus e to the negative, then you have a 1 over 4 plus n, then you have an x here this way. So let's do it this way. So you divide it by x, then you have your dx here. So now if you remember your Frullani integral, the one we discussed a week ago. We claimed that the integral from 0 to infinity of f of ax minus f of bx all divided by x dx is actually equal to f of infinity minus f of 0 times the logarithm of a divided by b. So this is the whole theory of Frullani integrals, and if you check the playlist, that is the first thing. We already proved this formula. Now of course this is dependent on the whether f of infinity exists, whether f of 0 defined, and all, and a and b of course have to be positive. So that is that. So then for here now, how do we tweak it? Well, we're going to break this into two integrals. Okay, we're going to first of all the first integral, so d to the negative ns divided by 2, so this will be equals to 1/4 of the sum as n runs from 1 to infinity of what? So you have the integral from 0 to infinity of what? You would have e to the 1/4 minus n then x minus e to the negative nx all divided by x dx. You can see that this is the form of the Frullani integrals. Then also you have the integral from okay, let me just put this sideways. So also now you would have the integral from 0 to infinity of what? Of e to the negative 1/4 plus n, yeah, e to the negative 1/4 plus n minus e to the negative nx all divided by x dx. So if you, let me zoom out a bit. Yes, this is better. So let me take this, let me clear this away. So let me quote the formula in box so you can keep it in mind. Let me put this color. So you, in box you have the Frullani integral, which is the integral from 0 to infinity of f of ax minus f of bx all divided by x, and this equal f of infinity minus f of 0 all multiply the logarithm of a divided by b. Okay, all right, so now that it's clear enough for us to see, let's observe that this is the form of the Frullani integrals we've been talking about. Now this is like here, this is more like f of x here. Wait, what am I doing? This is 1/4. Okay, I can write this as minus n minus 1/4. So I will do it that way. I'll do it as n minus 1/4 so that it will obtain the same form. So I'll write it as n minus 1/4. Okay, now notice that Frullani integrals insist that a and b has to be positive. Now here n minus 1/4 will always be positive because n is an integer, so it doesn't even matter whether n is 1. So n is a natural number, so it doesn't matter if n is 1, 2 or 7, it will always be positive. What about this case where everything here is positive, so it will always be positive? What about here? N here is positive and also n here is positive, so a and b are positive. And also f of infinity, of course, yeah, f of x here equals to e to the negative nx or something, e to the negative ax here. So f of x is always going to be, f of infinity and f of 0 is always going to exist. Okay, so in this case this satisfies the condition of the Frullani integrals. So what does that tell us? Well, this is 1/4 of the sum as n runs from 1 up until infinity of what? So here you would have to write this as f of infinity minus well, f of infinity on the other hand, like f of infinity is just e to the negative infinity, which is 0. So this will be 0 minus, what is f of 0? F of 0 is e to the negative 0 is just 1. So it's 0 minus negative 1. Because, okay, we're subtracting f of 0, right? How do I even place it? F of infinity is basically going to vanish to 0, because if you take e to the negative infinity, it is going to be 1 over e to the infinity, which is 0 with 0. So you have a 0 minus. Now, this is a e to the negative nx. So if you plug in 0 for x, so you have 1, okay? So you have a 1. You have a 1 here, so okay. And then you multiply this by the logarithm of n, so n minus 1 over 4 all divided by n. Then also you have a plus. Then in this case also you have a 0 minus 1 here. You multiply this by, let's go down. So you multiply this by the logarithm of n plus 1 over 4 all divided by n. So good things are happening. So now we finally got rid of the integral, and then we can now rest. So this is, you can take out the minus, so negative 1 over 4 times the sum as n runs from 1 to infinity of what. So here you have a logarithm of n minus 1 over 4 over 2. So you have n minus 1 over 4 divided by n. Then we are going to add this to the logarithm of n plus 1 over 4, n plus 1 over 4 divided by n. So if you multiply them out, you would have negative 1 over 4 times the sum. Negative 1 over 4 times the sum as n runs from 1 up until infinity of what? So you have a logarithm of n squared minus 1 over 4 squared all divided by n squared. So that should equal negative 1 over 4 times the logarithm of sum of as n runs from 1 to infinity of logarithm of 1 plus 1 minus 1 over 4 squared all divided by n squared. Now the sum of a log is the product of the logarithm, right? So this is going to negative 1 over 4 times the logarithm. So the sum of logs is the log of the product. So the logarithm of the product as of 1 minus 1 over 4 squared over n squared. And this is Wallis product. If you remember Wallis product, I have not discussed it on my channel, but I'm going to of course discuss it probably after this video. So this is Wallis product. This is going to equal negative 1 over 4 times the logarithm of sine of pi x, which is sine of pi over 4. You have a sine of pi over 4 all divided by what? All divided by pi over 4. So now this will be equal to negative 1/4 times the logarithm of, now sine of pi over 4 is square root of 2 over 2 all divided by what? Pi over 4. So we could probably do something from here. We'll get negative 1 over 4 times the logarithm of 1 over square root of 2. Then you have minus or then plus 1 over 4 times the logarithm of pi divided by 4, which is going to be 1 over 8 log 2 plus 1 over 4 log pi. Then you have a minus 1 over 2 log 2, right? Yes, log 2. So this is going to be if you subtract 1 over 8 minus 1 over 2, you get 1 minus 4 over 8, which is negative 3 over 4. So I think this is negative 3 over 8 log 2 plus 1 over 4 log pi. But essentially the problem is completely solved. So this should be the first time I'm using the Frullani Integrals on this channel. Yes, I have obviously proven the theorem, but this is the first video where I use this theorem to evaluate a definite integral. Of course, I'm going to see hundreds of videos from now on where this beautiful result was used to evaluate a definite integral. So thank you very much for staying with us, and please do enjoy your day. Okay, bye, and please subscribe to the channel. Thank you.